Hi, my name is Zheng from UC Santa Barbara. I'm very happy to introduce our work, DOTA, Detect and Omit Weak Attentions for Scalable Transformer Acceleration. This work is done at Scalable Energy Efficient Architecture Lab in UCSB with my colleagues and my advisor, Professor Yufei and Professor Yuan. Recently, transformer models have demonstrated excellent performance in various domains, including natural language processing, computer vision, and in some emerging applications like protein structure prediction and programming. A typical transformer model consists of a stack of encoders and decoders, where each one can be summarized into a three-stage processing procedure, namely linear transformation, multi-head attention, and feed-forward network. In our work, we focus on encoder-based transformers. The key to the success of transformer is the use of self-attention mechanism, which allows the model to evaluate interrelationships among the tokens to effectively understand input sequences. Specifically, the input to the self-attention mechanism are three feature matrices called query, key, and value. Each contains n feature vector where n is the number of tokens in the sequence. So we first compute Q times K transpose to generate the attention score matrix, followed by a softmax normalization to get the attention weight matrix. Finally, we multiply the attention weight matrix A with the value matrix to generate attention output. It is obvious to see that all of these three operations in the self-attention mechanism have quadratically scaled complexity with respect to the input sequence length n. To better understand the reason behind this, in our paper, we actually reinterpret the self-attention mechanism from a graph perspective. So let's use the sentence, I enjoy playing DOTA as an example. This sentence has 4 tokens. When it is processed by the self-attention blocks, each token is regarded as a vertex in that graph. So what self-attention does is essentially creating a fully connected and directed graph where each pair of tokens will have 2 edges. So the attention weights that we generated during the computation of self-attention are actually now the edge weights of the graph. So finally, as we want to update each token's feature, we will aggregate all the features from its incoming neighbors. So since the graph contains n squared edges, the complexity of self-attention will also be quadratically scaled. So this property of self-attention has made it the execution bottleneck of long sequence transformer inference. Our profiling results on a V100 GPU shows that this self-attention block could account for more than 73% of total execution time and more than 8.6 gigabytes of memory usage with a sequence length of 4K. So therefore, it is critical to reduce the cost of self-attention blocks in order to keep the scaling of transformer model to deal with longer sequence tasks. The key insight of our work is that we observe the attention graph to have many small edge weights that contributes very little to the final output. So these edges are called weak attention connections. A more intuitive demonstration can be seen from this figure as we randomly sampled several attention matrices from the squat benchmark. We can see that only very few attentions have weight values larger than 0.005, whereas most of the rest are close to 0. Another message from this figure is that the attention weight matrix is dynamically changing depending on the input sequence as well as different self-attention heads. Therefore, the attention sparsity is also dynamic. As we further run the model on the pruned sparse graphs, we are able to achieve very good accuracy while only keeping 10% of the attention connections. So these preliminary observations as well as the experimental results have indicated a huge potential of sparse transformer inference in terms of reducing the overall computation cost and memory consumption. But however, it is non-trivial to leverage such sparsity in the attention graphs. The first question is how to locate those weak attention connections. The most straightforward way is to obtain the attention weight matrix A first and then compare the values to select the important ones. So similar strategy can be applied to the attention score matrix because the softmax function does not change the relative value between different attention weight. Therefore, we can leverage this redundancy in the attention score matrix to make softmax and A times V to be sparse operations. We call this compute and then prune. However, you may already notice that this type of method requires computing the complete attention score matrix S, which is still of O n squared D complexity. So in other words, the scalability issue still remains. To fully address the problem, we want to introduce the sparsity before Q times K transpose so that all 3 stages of self-attention can benefit from the computation and memory reduction. Therefore, we need to detect and omit the weak attentions instead of compute and then prune them. To do so, we would require some kind of detection method to help us predict the dynamic sparsity prior to the computation of the self-attention. So finally, we also want the detection to be both efficient and accurate. On one hand, it should be accurate enough so that we don't incorrectly discard many important attention connections. On the other hand, we need it to be very lightweight and hardware efficient because it is considered as a extra overhead added to the self-attention mechanism. So if we want to keep its cost, so we have to keep its cost as low as possible. Otherwise, the benefit of sparse attention will be diluted by the detection overhead. And the hardware challenges are also critical to the sparsity-aware transformer inference. To start with, our system should support both detection and original execution because the detection and the transformer execution may have different type of operations. More importantly, the hardware should be able to efficiently process the sparse attention computation and deliver desired performance improvements. With the sparsity, the original dense gem operations and dense softmax are now different kind of sparse operators. For example, Q times K becomes the sample dense matrix multiplication, and the softmax function is now operating on a sparse matrix. And finally, the A times V becomes a sparse matrix multiplication as PMM. So in our experiments, we actually find that some of these sparse operators are difficult to accelerate on GPU, which motivate us to propose a customized architecture. So we have to experiment on state-of-the-art sparse GPU kernels provided by Google and cuSparse. We found out that in order to make the sparse kernels faster than gem kernels, dense gem kernels, we either need to enforce like very high sparsity ratio, or we need to have structured sparsity constraints in order to improve the data reuse. But the situation has been even more difficult as new generations of tensor core architectures have been proposed, delivering even higher and higher computation throughput for dense mixed precision computations. Therefore, the problem of GPU-based solutions is that we have very limited design space caused by the wrestling between performance and model accuracy. Basically, we cannot achieve satisfied performance improvements while maintaining a desired model accuracy. Therefore, in this work, we propose a top-down software hardware co-design solution, namely DOTA, that addresses all of the above software and hardware challenges. On software level, we propose to jointly optimize a lightweight detection network along with the transformer model to help detect and omit weak attentions. On hardware level, we propose a unified accelerator architecture for the detection and the transformer execution. And on top of it, we'll provide a complete data flow design, start with the workload distribution to the token parallel sparse attention data flow with computation reordering in order to efficiently support the sparse attention computation. So let's start with the algorithm proposed in DOTA. In general, we use a small detection network to predict the attention sparsity. Given the input matrix S, the detection network will multiply it with two weight matrices to generate approximate query and approximate key matrices. Then we can approximate the attention score based on these two approximate inputs. And we use the approximate attention score S to decide the attention connections to be preserved or discarded. So to control the cost of this kind of detection mechanism, we use low precision and low dimension computations for detection network. So first we will apply random projection to the input to reduce the feature dimension size. Then for both the input and the weight matrix used during the detection, we will use low precision data format, for example, in2 and in4. And then we formulate the training of the transformer model into a joint optimization problem. So as you can see, now the loss function contains two parts. The first is an end-to-end model prediction loss, and the second part is the mean squared error between approximate attention score and the actual attention score. And the two loss components are balanced by a hyperparameter lambda to flexibly control the training focus. And by jointly optimizing the detector and the transformer model, we can ensure both detection accuracy and final model accuracy. So with the above algorithm design, we propose the DOTA hardware system tailored for efficient dynamic sparse transformer inference. Let's start with the underlying architecture of DOTA. Each DOTA accelerator is a 4-lane architecture that can communicate with each other through an off-chip DRAM module, and on-chip accumulator is placed next to the compute lanes to add up the partial sums generated by different lanes. So the architecture can be easily scaled up or scaled out by increasing the hardware resources in each lane or by having more parallel compute lanes attached to the DRAM. So although different compute lanes can communicate with each other through the DRAM, we try to partition the transformer workload so that these off-chip interlane communications are minimized. In DOTA, this is achieved by mapping operations with independent input and weight and output to different compute lanes. For example, in the multi-head attention state, we can actually map different self-attention blocks to different compute lanes because they require completely different input and generate completely independent output. So please refer to the paper section 4.1 for more details regarding the workload partition and mapping strategy. Inside each compute lane, we reuse a single reconfigurable matrix multiplication unit for all the dot product related computations in different transformer layers and detection network. Other than that, the compute lane also contains other necessary hardware modules as well as an on-chip SRAM buffer to support both detection operations and transformer execution. Now we're going to highlight some important designs in our hardware system. The first is the RMMU. As mentioned, the RMMU is used for all the dot product-like operations. Therefore, a typical 2D processing element architecture is adopted. However, since the detection and execution may have different computation precision, our P array also need to support a row-wise precision configurability. In other words, we can have some rows of the P array work in high precision mode while using the rest of the rows in the P array to compute for low precision matrix multiplication used in the detection network. So the reason behind this unified architecture design is because for different user requirements and application scenarios, we may require different detector accuracy. For example, sometimes we need to be more accurate and then the overhead will be also larger, but sometimes we can make the detection network to be very lightweight so that very low precision computation are required. By using this unified architecture, we can dynamically balance the throughput of attention detection and transformer execution to enable a tightly coupled pipeline design. So as for the internal circuit design of each P architecture that enables such precision reconfigurability, please refer to our paper. Another important highlight of our design is the specialized token parallel data flow for sparse attention computation. Recall that we introduced dynamic sparsity to the self-attention block such that the dense operators are now sparse operators. Here we use Q times K transpose as an example to demonstrate our data flow. So the red color squares in this figure are the important ones to compute in the attention. To do so, we need different vectors from the query and key matrix and perform inner product between these vectors. And naive data flow, which is the one that adopted by prior work, is to compute the output matrix row by row from left to right. So as shown in this figure, we first use Q1 and K2 and K3 to compute the first row, and then we move on to the second row where Q2, K1, and K2 and K5 are needed. However, note that in actual case, the self-attention matrix is very large. So even we have loaded vector K2 in the first row, it is unlikely that our on-chip buffer can buffer all the K vectors used in the first row, and then we can reuse them during the second row. Therefore, we need to reload K2 again for the computation of the second row. Similarly, as we move to compute the third row and the last row, we always need to reload some of the key vectors. At last, in order to compute the final output matrix, we require in total of 14 vectors. So we need to traverse Q for only one time, but we need to constantly reload some of the key vectors. In our work, we argue that this kind of row by row data flow is suboptimal. It is because even for irregular distribution of the sparsity, we find there exist some fine-grained localities among the consecutive rows. In this example, many columns had three important elements. So this indicates a very good opportunity to reuse the key vectors for different rows. Based on this observation, we propose a token parallel data flow that is to compute the output matrix in group of rows. Suppose in this example, we process all 4 rows in parallel from left to right. Then in the first step, we will require Q1 to Q4 and K1, K2 to compute these elements. And then for the second step, as we move on, we can reuse the Q vectors, make them a stationary on chip, while we will need different K vectors to compute. Finally, in step 3, we only need K5 to compute the last 2 remaining elements. Using this type of token parallel data flow, the total memory access for computing the same output matrix is reduced from 14 vectors to only 9 vectors. So therefore, we use our data flow to improve the data reuse by using the attention distribution locality, which benefit overall memory access. So such improvement is very critical, very important to SDDM and SPMM because they are memory bounded operators. At last, let's look at the performance of DOTA. For our experimental setup, we first choose several representative benchmarks with various sequence lengths ranging from 384 to 4K. We choose NVIDIA V100 GPU and ELSA as the two baselines. So ELSA is the state-of-the-art accelerator that adopts a different attention detection method and a different architecture. So we experiment on two versions of DOTA. The difference is how much accuracy degradation we can allow. For DOTA conservative, we only allow 0.5% of accuracy degradation, while the DOTA aggressive can allow for 1.5%. So we implement DOTA in Verilog and synthesize the design using Synopsys design compiler using TSMC 22 nanometer standard cell library. Each DOTA accelerator consumes an area of 4.4 square millimeters and a power of 3 watts. So firstly, in terms of model accuracy, we compare DOTA with dense transformer models as well as ELSA. As we can see from the figure, across all the evaluated benchmarks, DOTA achieves on-par accuracy with the dense model under 90 to 95% of sparsity ratio. Also, we can see that under the same sparsity, DOTA achieves a much higher accuracy than ELSA, mainly by virtue of the trainable detection mechanism and the joint optimization strategy. So this figure shows the performance comparison between DOTA and the baselines. For a self-attention block alone, DOTA C achieves more than 100 times and 4.5 times performance speedup over GPU and ELSA respectively. For end-to-end transformer inference, DOTA C is also able to achieve an average speedup of 9.2 times over GPU. We also provide the latency breakdown of the dense transformer and the sparse transformer using DOTA, which shows two same things. The first is that the detection is negligible compared to the other parts. And also the second thing is with DOTA, the bottleneck of transformer has now been shifted from self-attention to linear transformation layers. As for energy efficiency, DOTA C achieves orders of magnitude improvements over GPU and 1.97 to 5.14 times improvements over ELSA. So for more breakdown analysis of DOTA's performance, please refer to section 5 of our paper. At the end of the paper, we provide sensitivity study over several hardware design choices in DOTA. So we use these sensitivity study as proofs to support these hardware configuration parameters. Please refer to our paper for more details. So to summarize, in this work, we propose to leverage weak attention connections to tackle the scalability issue of self-attention mechanism in long sequence transformers. So combining all the software and hardware techniques proposed in our work, DOTA is able to achieve orders of magnitude speed up and energy efficiency improvements over existing solutions. So that's all for my talk. Thank you very much for listening, and I'm happy to take any questions.